Alright, in this video I'm going to talk about continuity of a function and one-sided limit. Do you remember that when I introduced the limit of a function, if you want to find the limit of a function at the point A, what you do is you look at the height of the function left to A, and which is called the left limit, right? And height of the function right to A but very close to A is called the right limit. What is the notation for the left limit? The notation is limit x tends to A superscript minus and fx, right? And the right limit is limit x tends to A plus the superscript plus fx. It just tells you the left side or the right side of the limit. But if you are asked to find out the limit, left limit or the right limit, we do exactly the same way what we did to find out just a limit. What you do, you plug in that A into the x. Plug in the A into the x for both cases, okay? And to find out the functional value, also, you plug in A. You replace x by A and then find out. But one of the difference between finding the limit and the functional value is the function in the functional value you just plug in A. You don't simplify the function. You just replace x by A right away before you simplify it. But when you do the left limit and the right limit or the limit, you simplify first and then plug in the limit. I mean, you can try plugging in the limit at the beginning, and then if you get 0 over 0 or any kind of absurd form, then you can simplify and plug in back. But for the functional value, you plug in right away. For functional value, no need to simplify. To find out the limits, you may need to simplify. Sometimes the function will be already in the simplified form, so you don't have to simplify. But sometimes you need to simplify and then plug in the limits, okay? In this example, I am just looking at the graph and finding the limit. From the left, when you get close to A, the height looks like almost L. Right? From the right, when you get close to A, the height is almost look like L. And also at A, the functional value, meaning the height of the function at A is also L. So here, the left limit and the right limit and the functional value, all of them are equal. So if a function has these three things equal, we call the function is continuous at that point A. Okay? So what is the definition of the continuity of the function? Is if the left limit limit x tends to if the left limit, that means limit x tends to A minus fx, is equals to the right limit limit x tends to A plus the fx, is equals to the functional value at the point A, then we call fx is continuous at x equals to A. That's what we call, okay? If the left limit is equals to the right limit is equals to the functional value. And make sure that those limits and the functional value are finite, okay? They must be finite. Then we call that the function is continuous at x equals to A. You can look at from here to the function is continuous. There is no break, right? But mathematically, we don't look at the break or not. We don't draw the graph. But what we do usually is we can tell whether the left limit is equals to the right limit is equals to the functional value or not. And then we can decide whether the function is continuous or not. Let us look at this example, okay? On this example, find limit x tends to 2 minus fx. If you go to 2 from the left side, what is the height? It looks like the height is almost equals to 3, right? So it will be 3. How about limit x tends to 2 plus fx? If you go to 2 from the right side, okay, the height is almost equals to 3. This is also 3. And what is the functional value at 2? At 2, the height is actually 3. Since these three are equal, then the limit exists, okay? So for the limit existence, you need the left limit and the right limit equal. For the continuity, we need all these three things equal. So the limit exists, yes. What is the limit? The left limit and the right limit are equal to 3. So the limit is 3. You see that? Is the function fx continuous at x equals to 2? Since the left limit, right limit and the functional value are equal, the answer is yes. If the left limit, right limit, and the function value are equal, then we call the function is continuous at that point. Okay. Let us look at another example. Here, this is that graph of the function is in the green. Okay, at -2, we have -2, -2. But you see that at that point there is a open circle. There is an open circle. That -2, -2 is an open circle. Okay. Now look at that. Is the left limit? What is the left limit? We are going to -2 from the left side. Okay, right here. So it looks like the height is almost equals to -2, right? How about from the right side? If you go to the -2 from the right side, the height is almost equal to -2 again. How about the f at -2? Meaning, what is the height of the function at -2? Since it is the open circle, okay, does not exist, dne. So the functional value does not exist. How about the limit? Do you think the limit exists? The limit exists because the left side and the right side are equal. So the answer is yes. And what is the limit? Since these are both of the heights from the left and right are equals to -2. So the limit is -2, but the function is not continuous. Why? Because the limits, the left limit and right limit, and the functional value are not equal. So the answer is no. Okay. Let us look at this example. The graph is like this. From -1 and left, the height is -1, right? It is below. From -1 and from right to the -1, at -1 the height is -1, but right to -1 the height is +2, right? What is the left limit for this function? It is -1, right? The height towards the left of -1 is -1. What is the right limit of at -1 is from, if you go to the -1 from the right, it looks like the height is almost equals to +2. So actually it is equals to +2. So the limit are not equal. You see that? Limit are not equal. How about the functional value? What do you think? To look at the height at -1, you look at -1 here because there is a closed circle, right? So at -1 is defined on this function. So anything right to -1 is defined on that function. So it is -1 as well. Do you think the limit exists? No. Right? The limit does not exist because the left limit and the right limit are not equal. How about the continuity? No, because the limit does not exist. Also the functional value is not equal to the left limit and right limit. So the answer is no. So from this you can say that if a function is continuous, then all these three quantities must be equal, right? All these three quantities must be equal if the function is continuous. But if the limit exists, the function may or may not be continuous. In this example, the limit exists, but the function is not continuous. Okay. On this example, the limit exists and function is continuous. Here, the limit exists, but the function is not continuous. Here, limit does not exist, so function is not continuous. From here, you can say that if a function does not have a limit at a point, then the function is not continuous at that point. Okay. Now let us do one more example on how to find out the right limit here. So again, to find out the limit, you need to simplify first. If you plug in right away, you will get 9 over x plus 0. That is 9 over x minus 9 over x is 0 over, if you plug in that 0, 0 over 0. So that's not the answer. So we need to simplify first. So what you do is you make the same denominator on the top, or you combine these two fractions. Okay. So what you do is limit delta x tends to 0 plus. Okay. So so what is the product of the denominator of the top function? X times x plus delta x. So what you do the cross multiplication like that, right? So it is 9x minus 9 times x plus delta x, and then divide by delta x there, right? That whole divide thing is here. Okay. So how do you simplify that? On the top, you can write 9x minus 9x minus 9 delta x. You see that? Divide by x times x plus delta x, and then divide by delta x there, right? So you can cancel out that a positive 9x and negative 9x. And if you want to simplify this fraction, there is like one fraction on the top and another fraction at the bottom. That bottom fraction has 1 in the denominator. So what you write is limit delta x tends to 0 plus, right? And that is negative 9 delta x over x times x plus delta x times times 1 over delta x. You see that? Because when you write the simplified form of the two fractions, you write the top fraction times the reciprocal of the bottom fraction. Okay, now you cancel out delta x and delta x. What is left is negative 9 over limit delta x tends to 0 plus, right, negative 9 over x times x plus delta x. You see that? Although there is 0 plus, basically it is 0, but it is saying from the right side. So basically you plug in 0 there. Limit, it is same as delta x tends to 0, negative 9 over x times x plus delta x. Now you plug in that 0 plus or 0, whatever you want to say, but this is basically 0. So you plug in 0 here. So what you get is negative 9 over x squared. That's what you get. And again, after you plug in the limit, you don't need to write limit again. Okay, after you replace delta x by 0, you don't need to write the limit delta x tends to 0 again. So this is the final answer. So the limit here is negative 9 over x squared. Okay, so let us do another example. In this example, I discuss the continuity of fx equals to x squared minus 1 over x minus 1. If you remember from college algebra, you see that how do I find the domain of a function? Domain of a function is the x values, okay, where the function is defined, okay, meaning that to find out the domain of the function, we try to avoid these x value that gives you infinity for the function, okay. For example, if there is x in the denominator, you solve that denominator and find out the x value and then say that the domain is all x except that you got from solving the denominator. If there is a root, you try to get the values of x that give you the positive value under the root, right? And you exclude the other values of x that give you the negative under the root. So similarly, since for continuity of a function, we need to have the left limit, right limit, and the functional value equal. But what is the function value? Look at this. The function is a line, the graph is a line, left of 1 the graph is a line, right of 1 the graph is a line, but at 1 there is a hole. Why? Because if you plug in 1 here, you will get 0 over 0. You see that? If you plug in 1, you will get 0 over 0, which is not good because the graph is, the function is not defined at x equals to 1. But everywhere except 1, the function is defined. You see that it is continuous. At 1 it is not continuous. So you see that, so the function is not continuous, so fx is not continuous at x equals to 1 because f1 does not exist. You see that? Because the f1 does not exist. Okay, now there was a graph, so it was easy to see that there is a hole there, right? If there is no graph, how do I find out where the function is not continuous or where the functional value is not defined? The idea is, if there is a denominator, if there is x in the denominator, you solve that. How do I do that? You do x minus 1 equals to 0. This implies x equals to 1. So the function is not defined at x equals to 1, meaning the function is not continuous at x equals to 1. This is all I find. Okay, so if there is a root under, then you try to find out x values that does not give you the negative values. Okay, so you solve it or write the thing under the root greater than 0. That is the place that the function is continuous. In other places it is not continuous. Let us look at this exercise, this example. So there is no graph, right? But there is x in the denominator. How do I find out the points or the x values where the function is not continuous? Is you do 64 minus x squared equals to 0, right? Add x squared on both sides. You get x squared equals to 64. Take the root. When you take the root, though, you need to do plus and minus both, right? So you get x equals to plus minus 8. So this function is continuous everywhere except at positive 8 and negative 8. So continuous everywhere except x equals to 8 and negative 8. This is the answer for that. Okay, so this function is not continuous everywhere. It is continuous everywhere except negative 8 and positive 8. This function is also continuous everywhere except x equals to 1. Let us talk about some of the functions that are continuous everywhere, okay? All the polynomial functions are continuous everywhere, meaning what type of functions are polynomial functions? If there is no x in the denominator, okay, and if all the x's have a positive exponent or 0, positive whole number exponent, positive whole number, okay, or for example x squared plus 5x, x cubed plus x squared plus 9x, all those are polynomial functions, okay. Linear functions, quadratic functions, cubic function, all those are polynomial functions. Some trig functions, for example fx equals to sine x, fx equals to cosine x, are continuous everywhere, but the fx equals to tangent x is not continuous, okay, because fx equals tangent x is infinity as at pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so on, okay. So all the trig functions except all the sine functions and cosine functions are continuous everywhere, okay. Next, if a function is not continuous at x equals to a, we call it discontinuous there, okay. There are two types of discontinuity. One type of discontinuity is removable. We call removable discontinuity, meaning the limit exists but the functional value either may not exist or it is not equal to the limit, okay. If the limit exists but the functional value is not equal to the limit, because left limit and the right limit equal means the limit exists, right? Limit exists but the functional value is not equal to the limit. That is called removable discontinuity. And non-removable is if the limit does not exist, then we don't worry about the functional value. If the limit does not exist, then it is called non-removable discontinuity, okay. In case of the removable discontinuity, in this case what we do is in case of the removable discontinuity, we can make it continuous by redefining the functional value. We will see an example. This is the example for that. Again, in case of the removable discontinuity, meaning if the limit exists, then we can make the function continuous by redefining the function value. Suppose the function is not continuous, but the limit exists, meaning the functional value is not equal to the limit of the function, okay. In that case, we will be able to redefine the function and then make it continuous. Let us see this example. Let us see the solution, okay. So we want to check the continuity of this function. So to find out the left limit x tends to 1 minus, which function should I pick? Left to 1. Left to 1 means at 1 the value is 3, the height is 3, but left to 1 everywhere except 1 is this value. The function takes this value, right? So what you do is x squared minus 1 over x minus 1. When you plug in the limit though, although it is 1 minus, you plug in 1. You understand that? Because this is just a notation saying that we are going to 1 from left side. So if you plug in 1 directly, you will get 0 over 0. So you don't want to plug in right now, okay? What you do is limit x tends to 1 minus. So get the factors of the top. X minus 1, x plus 1. These are the two factors over x minus 1. So you got the same factor on the top and bottom. You cancel that out. What is left is x plus 1, right? Limit x tends to 1 minus x plus 1. Although it is 1 minus, you just plug in 1. So you got 2. So the left limit is 2. How about the right limit? Limit x tends to 1 plus x squared minus 1 over x minus 1. You do exactly the same thing and then get limit x tends to 1 plus and then x plus 1, right? When you plug in, you just plug in 1, so that is 2. How about f at 1? F at 1 is 3. So the limit exists. Left limit and the right limit are equal. They exist. The limit exists. But the functional value is not equal to the limit. So the fx has removable discontinuity. Removable discontinuity at x equals to 1. But if you want to, you can redefine. You can redefine the function like this. You can redefine fx equals to, if you define x squared minus 1 over x minus 1, you cannot change the piece that has x, okay? If x not equals to 1 and then 2 if x equals to 1. If you define like this, you will have left limit and right limit equal and the function will be continuous. So for the removable discontinuity, you can remove the functional value and replace by a number that is equal to the limit. You see that? And then you can make it continuous. But when you have a removable discontinuity, you can replace the functional value only. You cannot change this function to make it continuous. Don't change this function that has x. Only change a number only. If there is a separate number there, then you can change and make it like this one doesn't have x, right? So you could change this 3 to make 2 and then define it as a continuous function. But if it has like 3x, you will not be able to do that. You cannot change it. You will say it is non-removable discontinuity. You understand that? Let me take a couple more examples. Let us see this example that has again the piecewise function. Okay, what does it say? Fx equals to negative 5x if x is lesser or equals to 2, and for x greater than 2 it takes this value. Okay, both of these p's have x. Okay, now you see that this is a polynomial function. This is a degree 1, right? This is a linear function. This is a quadratic function. So they must be continuous everywhere in their domain, but the domain is all the values less than or equals to 2. This is that function, and for x greater than 2, this is that function. So this function is continuous everywhere, but we want to check, and this function is continuous everywhere in its domain too. But here the boundary is 2, right? On the left of 2, it takes this value. On the right of 2, it takes this value. At the boundary, now we doubt on the boundary. On the boundary, it may not be continuous. We will check. Okay. So how do I check that? Is we find out the left limit. So solution is, let's find out the left limit at 2. X tends to, so x tends to 2 minus. Okay. Because at 1, 0, negative 1, negative 2, negative 3, it is continuous because it is a polynomial function. At 2 may not be because this function go up to 2 only. And after 2, on the right of 2, another function starts. So they may have limit may not exist, or the functional value may not be equal to the limit. So we want to check that. But everywhere except 2, the function is continuous, okay? Because they are the polynomial function. So fx, so I want to find out the left limit of the function fx. What I do is limit x tends to 2 minus, which p should I pick? Left means all x less than 2. So you need to pick this negative 5x. Okay, although this is 2 to the negative, you just plug in 2, so that will be negative 5 times 2. You don't plug in negative 2 because it is 2 minus means it is 2, but from the left side slightly smaller than 2 might be. That's why I just put almost 2. So negative 5 times 2 is negative 10. The left limit is negative 10. How about the right limit? Limit x tends to 2 plus fx is, so limit x tends to 2 plus, which p should I pick? The second, right? Because all values of x greater than 2, this is the function. So you do x squared minus 4x plus 7. What you do is you plug in that 2. So 2 squared minus 4 times 2 plus 7. How much is 2 squared? 4 minus 8 plus 7 is how much? Is that 4 minus 8 is negative 4 plus 7 is 3. So the left limit is not equals to the right limit. So the limit does not exist. So limit does not exist means the function is not continuous. Although you can find out what is f at 2. What is the functional value? Which piece should I pick for the functional value? You are right, the top piece, because it says equals to 2. X is less than or equals to 2. Equals to 2 means that is the place, that is the piece you pick the functional value. That is negative 5 times 2 equals to 10. So the limit does not exist. They are not equal, right? This is not equal to that one. So the limit does not exist means the function is not continuous. So basically it has non-removable discontinuity. So not continuous. I would say non-removable discontinuity. So if the function is not continuous, then you may want to decide whether it is removable discontinuity or non-removable discontinuity. All right, let us do this example. If fx is continuous everywhere, it says the function is continuous everywhere. Okay, then find a and b. So if the function is continuous everywhere, it must be continuous on those boundaries too. So what we do is there are a and b. Okay, so the left limit at 2, let's check left limit at 2. So since it is continuous, limit x tends to -2 minus fx is equals to limit x tends to -2 plus fx. You see that? Because they are continuous, so the limit must exist. Okay, the limit must exist because they are continuous. Now let's plug in that. So which function should I pick for the left limit at -2? 6, right? So this value is 6. You see that? Because for the left limit you pick this function, there is no x, so you don't have to plug in that -2 minus, just write down 6. On the right limit at -2, this is the piece where the right you go from -2, you go to -2 from right. Okay, so it is a times -2, a times you plug in that -2 plus b. So what do you get? You get 6 equals to negative twice a plus b. That's what you get. Do you understand that? Okay, so the next thing I want to do is let us check the continuity at +4. For +4, so limit, why do I know that they are equal? Because it says the function is continuous everywhere, so it must be continuous at -2 and +4. Limit x tends to 4 minus fx must be equals to limit x tends to 4 plus, or you can just write down the f4 also, that is also fine. F of x. What is 4 minus fx? Which piece should I pick? I pick this piece, right? And then you plug in x equals to 4. So 4a plus b equals to, there is -6 on the right, because for x greater or equals to 4, you pick that piece. Now you got two equations, right? Equation 1 and equation 2, right? So equation 1 and equation 2. So this is equation 2. Now you solve those two equations. How do I solve? You add or subtract, right? Let me subtract the second equation. There is negative twice a plus b equals to +6. I want to subtract. Subtract means subtract this and then subtract that. You cancel out. You cancel out those two. What do you get? 4a plus 2a is 6a equals to, you are also subtracting here, right? -12. So what do you get? You get divide by 6 on both sides. You get a equals to -2, right? And to find out b, let me continue here. So you plug in one of the equations. So let me use a equals to -2 in equation 2. What do you get? You get 4 times -2 plus b equals to -6, right? So -8 plus b equals to, you get -6. Now add 8 on both sides. What do you get? Add 8 on both sides. You will get b equals to +2. So a is -6 and b is +2. That is the values of a and b. So that if you plug in -2x +2, then the left limit and the right limit at -2 and the left limit and right limit at +4 are equal.